Jai Hind everybody. My name is Nandita Goyal. I am working as an assistant professor in Department of Information Technology at AKGEC Engineering College. So today I'll be discussing the topic relation and its type in context of discrete mathematics. The topics which I'll be covering for today include ordered pair, Cartesian product, properties of Cartesian product, what are the various relations and along with examples, and what are the different types of relations which we discuss in discrete maths. So starting with ordered pair, what exactly is an ordered pair? Because whenever we try to understand relation, first of all we need to understand what exactly an ordered pair is. So if we talk about ordered pair, it is a pair of objects where the order in which the component occurs is very important. So if I am talking about two sets A and B and I am talking about an ordered pair A comma B, that strictly means that all the components A should belong to the set A and all the components small b should belong to the set capital B. And when we write these components, in this order along with a comma which is separating both the components and enclosed within parentheses. So let's take an example. Suppose I have a set A which contains 3 elements 1, 2 and 3. I have another set B which contains 2 elements A and B. Now I want to write all the ordered pairs for these two sets. So what I have to do, I'll take the elements of set A, then I will put a comma and then the element of set B. So this becomes one of the ordered pair. Another ordered pair which is possible, I can take the element 2 along with the second element from set B, that is small b. Another possibility is I take 3 and along with 3 I can take A, I can even take B. So all these are ordered pairs where we take the first component from set A and the second component from set B. So this is what we call a ordered pair. Now next, talking about the Cartesian product. So the term Cartesian product actually comes from ordered pair. If we have two sets A and B and I talk about the Cartesian product, we usually represent it as A cross B. Now what is this Cartesian product? This actually contains all the ordered pairs A comma B such that the element small a should belong to the set capital A and the element small b should belong to the set capital B. So let's take an example. If I have a set A which contains 2 elements 1 and 2, I have another set B which contains the elements A and B. Now A cross B will contain all the ordered pairs which are possible for these two sets. So one possibility is we can have 1 comma A, another possible ordered pair is 1 comma B, then we have 2 comma A and 2 comma B. So these are all the possible ordered pairs for these particular set. So this is what is known as Cartesian product, where we have all the elements that can belong to the ordered pairs. Now there are a few properties of Cartesian product which usually hold for all the sets. Now suppose we have 4 sets A, B, C and D and I apply A intersection B, then C intersection D and I take the Cartesian product of these two sets. So this result will be equal to A cross C intersection B cross D. Here cross is nothing but it denotes the Cartesian product. Similarly, we have a second property which means that A minus B, if I am calculating the difference for two sets A and B and then I take the Cartesian product with another set C, this is same as A Cartesian product C minus B Cartesian product C. The third property says that if I have two sets A and B and I take the union of these two sets and then I take the Cartesian product along with set C. This is same as A cross C, that is A Cartesian product C union B Cartesian product C. The fourth property says that if I have two sets B and C and I take the intersection of B and C and then I take the Cartesian product with A, this is nothing but it is equivalent to A cross B intersection A cross C. So, all these four properties will always hold for Cartesian product. Now, coming to relations, what is a relation? So, in order to understand a relation, we should have the knowledge of ordered pairs as well as Cartesian product, because a relation is nothing but it is actually a subset of the Cartesian product of any two sets A and B. So, if you have any two sets A and B and I take the Cartesian product A cross B for those two sets. So, what I'll get all the ordered pairs which are possible for set A and B. Now, what will be a relation? A relation will always be a subset of this Cartesian product, but it will contain only those elements which will actually comply to the property of the relation. So, whenever we denote a relation, we denote a relation with the notation ARB, where ARB means that A comma B ordered pair belongs to relation R. Suppose a relation is not possible for two components A and B, then we denote it as A not related to B. This R cross means not related, and this is used to denote that A and B do not belong to the relation R. Let's take an example. Suppose I have a set A which contains three elements A, B and C. I have another set B which contains the elements 1, 2 and 3. Now, if our relation is defined as A comma 1, B comma 2 and C comma 2, we have to tell that will this be a relation from A to B? Yes, this will be a relation. Why? Because see, the first component or first element contains A which belongs to set capital A, and the second component is 1 which belongs to set capital B. Same way, if we move to the second element, it contains B comma 2. So, this small b is a element of set A and 2 is an element of set B. So, again this qualifies for the relation. And third element, if we check the third element, it contains first component C which is part of set A and then 2 which is part of set B. So, we can say yes, this is a relation from A to B. So, this is justified. Now, if we talk about the next relation which is denoted by Q. So, Q contains 1 comma A. So, is it a relation from A to B? No. Why? Because if it is a relation from A to B, it should always contain the first component from set A. But here if I talk about this 1, this is from set B and the second component A is from set A. So, this cannot be a relation from A to B. Now, let's talk about the last relation, that is denoted by this capital P. So, if capital P contains A comma B, A comma A, B comma C, B comma A, is this a relation from A to A? But here we have changed, it is not from A to B, it is asking us, is it a relation from A to A? That means we are making use of only set A. The first component will also belong to set A and the second component will also belong to set A. So, if I talk about the first element, that is A comma A, it has both the components which belong to set A. Now, coming to the second element, if I talk about B, B belongs to set A and C also belongs to set A. So, this is also okay. Now, third element, that is B comma A, both are the elements from set A. So, yes, P is a relation from set A to A. So, this is how we can define a relation. Now, whenever we talk about a relation, we have two terms associated with a relation, that is domain of a relation and range of a relation. So, if I talk about the domain of relation is nothing but when I am taking the ordered pairs, each ordered pair is made up of two components, that is the first component and a second component. So, if I take a set of all the first components of the ordered pair, then it basically forms domain of the relation. And if I take the set of all the second components of the relation, then it forms the range of the relation. So, these are the terms related with a relation. We will even take an example to understand this. Suppose I have a set X which contains 5 elements, that is 1, 2, 3, 4 and 5, and I have another set Y which contains 3 elements 4, 5 and 6. Now, what is the definition of the relation? There will be a relation R which is defined from set X to the set Y. So, that means the first component has to be from set X and the second component will be from set Y. Now, the definition of the relation says that it will contain all the X comma Y pairs if X will be greater than Y, such that small x should belong to capital X and small y should belong to capital Y. Now, see, if I want to list down all the pairs in the Cartesian product, so we will have a number of pairs in the Cartesian product which will have 1, 4, then 1, 5, 1, 6 and so on. Even we will have 4, 4, then 4, 5 and 4, 6, so on and till the last element. But here we don't need to find the entire Cartesian product. The relation which we need to find is only those pairs where your X will be greater than Y. So, if I take the components of X, which is that pair for which X will be greater than Y. So, if I compare 1 with any element in Y, it will always be small. Same way with 2, same way with 3. Even for 4, it is equal to 4, but in relation it is clearly mentioned that X should be less than Y. So, we can only have this 5. So, if I compare this 5 with 4, so that means 5 will be greater than 4. So, this is the only pair which will be present in the relation. So, I can write my relation as having only a single pair of elements, that is 5, 4, because this condition is satisfied only for this single element. Now, for this particular example, if I talk about the domain and range of this relation. So, for domain, you have only one element here, which is nothing but 5. And for range also, you have a single element here, which is 4. So, this is what is domain and range. Now, by this time, we were talking about relations on two different sets, a set A and a set B, where we were saying that the ordered pair A comma B, A has to be from set capital A and small b has to be from set capital B. Now, we will be talking about a relation on a single set. Now, suppose I have a single set A for which I want to define a relation to itself. How I can do that? Now, let us take an example. Suppose you have a set A which contains 4 elements, 1, 2, 3 and 4, and the relation is defined with the name RDIF. It is equivalent to, it will contain all the A comma B pairs such that A divides B. So, we will have to check that only if A divides B, then only that pair can be included within the relation. So, let us see. Now, since the relation is defined from itself, what all elements it can have? It can have elements 1, 1, 1, 2, 1, 3, 1, 4. Then 2, 1, 2, 3, 2, 4. Same way 3, 1, 3, 2, 3, 4 and 3, 3. 4, 1, 4, 2, 4, 3 and 4, 4. So, the Cartesian product will contain all the elements, but when I want it to be in relation, I will see that whether the property A divides B is satisfied or not. So, since 1 divides every element, so we will have 1, 1, 1, 2, 1, 3, 1, 4. Okay. Now, if I talk about 2, 2 will divide 4 and 2 will divide even itself. So, 2 divides 2 and 2 divides 4. If I talk about 3, then 1 divides 3 but 3 does not divide 1. So, neither 3 divides 2 nor 3 divides 4. So, nothing can be there where 3 can be the first component. Then, if I talk about, but one component can be there 3, 3 because 3 divides 3. Same way, if I talk about 4, then we can have 4, 4. So this is the relation for A divides B. Now if I want to talk about the domain and range here, what will be the domain for this relation? All the first components, that means I'll have 1, then I'll have 2, even 3 and 4. And if I want to talk about the range, the B components, set of B components, that is 1, 2, 3 and 4. So the domain and range is the same, and it is same as that of set. Now we have another example. We have a set A which is going to have a relation on itself. So A contains 1, 2, 3 and 4, and we define the relation R not equal to as if there will be elements in this relation only if A is not equal to B. So this relation R not equal to will contain what all elements? We have to see that A should not be equal to B. Only the condition is this. That means it won't have any diagonal elements. Diagonal elements means where the first and the second components are same, that is A comma A elements will not belong to this relation are not equal to. Other all the ordered pairs will be there. So it will contain 1, 2, 1, 3, 1, 4. Then it will have 2, 1, then 2, 2 cannot be there, 2, 3 and 2, 4. It will even have 3, 1, 3, 2, 3, 3 cannot be there, so it will have 3, 4. And the last 4, 1 will be there, 4, 2 will be there and 4, 3 will be there. 4, 4 cannot be there. So if we just remove the diagonal elements, that is all the elements of the form A, A, the remaining elements will be there in this relation. So if I talk about the domain of this relation, what will be the domain of this relation? The domain will contain all the 4 elements 1, 2, 3 and 4, and the range will again contain all the elements 1, 2, 3 and 4. Now if I want to ask this, that what will be the cardinality or what will be the number of relations which are possible on a set A with cardinality n. Cardinality means the number of elements in the set. So we are saying that if a set A has n elements, then on this set A, how many total relations are possible? Now let's see how can we calculate this. We have a set A which contains n elements 1, 2, 3 up to n. If I talk about the Cartesian product of A cross A, how many elements will it have? A cross, since A is having n elements, A cross A will have n square elements. Now what is a relation? A relation is nothing but a subset of Cartesian product. We know this by the definition of a relation. Now if I have n square elements, then with these n square elements, how many subsets are possible? How many subsets we can make? So number of subsets is equal to 2 to the power n square. So that means a total of 2 to the power n square relations are possible for a set A which is having a cardinality n. Now this is even an example where we have calculated the number of relations which are possible. I am having a set A which contains 2 elements 1 and 2. If I write the cross product A cross A, what all will be there? 1, 1 will be there, 1, 2 will be there, 2, 1 and 2, 2. So these are all the elements in A cross A. Now we want to list down the possible relations, that is all the subsets of A cross A possible. So for this particular example, one subset which is possible is phi, because phi is a subset of every set. That is, an empty set is always a subset of every set. This is the property of sets. So phi is one subset. Then talking about the next class of subsets with a single element. So 1, 1 can be there, 1, 2 can be there, 2, 1 and 2, 2. So here we have 4 possibilities. So 4 subsets are possible. If we have combination of 2 elements, so with combination of 2 elements, if I list down all the subsets, a total of 6 subsets are possible. Now taking a combination of 3 elements, for 3 elements I can form a total subsets 4. And then with all the elements, all the 4 elements, there is only a single subset which is possible, that is nothing but A cross A itself. So that is one subset. Now if I sum up all these subsets, I get a total of 16 subsets. Now what I had calculated, that was the number of relations possible is equal to 2 to the power n square, where n is the number of elements. So now if I calculate by using this formula, it means that since n is equal to 2, so n square becomes 4 and 2 to the power n square becomes 2 to the power 4, which is nothing but 16. So that means 2 to the power n square relations are possible for a set A containing n elements. Now coming to the types of relations, there are different types of relations which are possible. So coming to the first relation, identity relation. So what is an identity relation? An identity relation will only contain A, A elements. Like we have a set A which contains 3 elements A, B and C. If I want to define the identity relation on this set A, so it will contain only the diagonal elements, that is A, B, B and C, C. So this will give you the identity relation I, which will contain all the A pairs for every A that belongs to A. Similarly, if I have a set A that contains 2 elements 1, 2, and I want to find out the identity relation for this set A, this will be nothing but the combination of all the diagonal elements, that is 1, 1 and 2, 2. So this is what is known as a identity relation. Now talking about the inverse of a relation. Inverse of a relation is seen as a set that has elements which are inverse pairs of another set. Like I'll take an example. If I have a relation R which contains the elements A, B and C, D, then its inverse will contain the same elements, but the order in which their elements are occurring will just change or will just inverse. So R inverse will contain B, A and D, C. This is what is your R inverse. R inverse is equal to B, A and D, C for this particular example. So in general, if we define R inverse, this is nothing but B, A such that we have a B pair which belongs to relation R. So this is known as inverse relation. Now the next type of relation is reflexive relation. In a reflexive relation, what happens? We can say that a relation is reflexive if it contains the diagonal elements. It should have the diagonal elements, although it may or may not have any other elements. So if I have a set A which contains 2 elements, that is 1, 2. So it should have at least 1, 1 and 2, 2 for this relation to be reflexive. If a relation contains these diagonal pairs, we call it as reflexive, and this relation may or may not contain other elements. Like here it is containing 1, 2 and 2, 1 as well, but it is reflexive because it is containing these 2 elements. If these were not there, then it cannot be reflexive. For a relation to be reflexive, it should have a minimum of A pairs. We can even take another example. If I have a set A which contains A, B, then for a relation to be reflexive, I can have a number of reflexive relations which are possible. A, and B, B should be there. So this relation is reflexive even if I add certain more elements to this, like A, B. Even this is reflexive because it is having these 2 pairs. Whatever else it is having, that is not a problem, but it should have a minimum of these diagonal elements. So now if we just want to know that what will be the cardinality of smallest and largest reflexive relation which is possible. So talking about the smallest reflexive relation possible, whenever we are talking about reflexive relation, it must have the diagonal elements, at least the diagonal elements, that is minimum we need to have the diagonal elements. So if I have a set A which contains 1, 2 up to n, so how many diagonal elements will be there? If I write down the cross product A cross A, it will have 1, 1, then 1, 2 up to 1, n and so on. Same way I'll have 2, 1, 2, 2, 2, n. Same way I'll have n, 1, n, 2, n, n. So if I talk about the diagonal elements, these are my diagonal elements. So this relation should have a minimum of these diagonal elements. That is, how many diagonal elements will be there? If my set has a total of n elements, diagonal elements will also be n. So the smallest reflexive relation will have at least how many elements? It will have at least n elements. And what about the largest reflexive relation? That means we'll have these diagonal elements, but along with this, what maximum we can have? So if I take this entire A cross A, this will always be reflexive because it will contain all the diagonal elements, as well as it will have a maximum number of elements which are possible. So what is the cardinality of A cross A? N square. So a maximum of n square elements are possible. So largest reflexive relation will have a cardinality of n square. Now we want to check that how many reflexive relations are possible for a set with cardinality n. If that means if a set A has a total of n elements, then how many reflexive relations are possible? So we'll start with a small set A which contains only 2 elements, that is 1 and 2. So for such a small set, we'll see how many reflexive relations are possible. So we are saying that if this relation is to be reflexive, it should contain all the A, A elements. That means for this particular example, it should at least contain 1, 1 and 2, 2. So this R1 is the smallest reflexive relation which is possible for this set A with 2 elements. Now I'll keep on adding the elements to it to check how many reflexive relations are possible. I have just added a single pair 1, 2 to the previous relation R1. So I get a new relation R2 which is again reflexive. Now R3, in place of this 1, 2, I have added 2, 1, and again this R3 is reflexive because it contains the diagonal elements. Now coming to the relation R4, I have added both the elements, that is 1, 2 and 2, 1 other than the diagonal pairs. So this is again reflexive and this is nothing but actually A cross A. So if I have these 2 elements, how many reflexive relations are possible? A total of 4 reflexive relations are possible. Now if I see this A cross A, for this particular element 1, 1, how many choices I have? I have only one choice, that is to include this element, otherwise I won't get a reflexive relation. Similarly, if I check with this element 2, 2, how many choices I have for this element? I have a single choice, that is to include this element, because if I will not include this element, my relation will not be reflexive. Now if I talk about 1, 2, for this 1, 2, how many choices I have? I have 2 choices. I may include this element or I may not include this element. Same way for 2, 1, how many choices I have? I have 2 choices, that is I may include this element or I may not include this element. So for 2 elements I have 2 choices, so that means 2 to the power 2 which is 4. So a total of 4 reflexive relations will be possible here. Even we have seen that R1, R2, R3 and R4. Now we'll be talking in general. If my set A has n elements, that is 1, 2, 3 up to n, then how many reflexive relations are possible? Then again we'll see A cross A will contain 1, 1, 1, 2 up to 1, n. Same way it will continue 2, 1 up to n, n. Now, the same Cartesian product, I can list down, I have taken all the diagonal elements on one side and then separated by commas, I have taken all the other elements. So, if I talk about these diagonal elements, how many diagonal elements I have in total? I have a total of n diagonal elements. And then these remaining elements, how much will be these remaining elements? I already know that my A cross A has n square elements. That means all these elements are equal to n square, out of which these are n elements. So, these remaining elements become n square minus n elements. Now, if I talk about the diagonal elements, how many choices I have for these diagonal elements? I have a single choice, that is to include each diagonal element, because otherwise my relation is not going to be reflexive. But for these n square minus n elements, how many choices I have? I have two choices for every element. Why? Because I may include these elements or I may not include these elements. This will not affect the reflexive nature of my relation. So, since I have two choices only for these n square minus n elements, so how many reflexive relations I can have? 2 to the power n square minus n. So, this is the number of reflexive relations which are possible for a set A with cardinality n. Now, coming to the next type of relations, these are known as symmetric relations. So, when can we say that a relation is symmetric? Suppose I have a set A which contains the element 1, 2 and 2, 1. This is the relation which is defined on a set A which is having two elements 1, 2. Now, since we are having a pair A, B, that is 1, 2, then I need to have the pair B, A for this. Whenever I have a pair A, B which belongs to a relation, then we must have a pair B, A which should also belong to the relation for it to be symmetric. Okay. So, if I talk about this relation R, where R contains 1, 2 and 2, 1, then this is a symmetric relation. So, we can have a number of symmetric relations which are possible. But if I talk about the cardinality of smallest and largest reflexive relation, now suppose I have any relation which doesn't contain any element, it is just a empty set. What can I say? Is it a symmetric relation or not? Yes, it is a symmetric relation. Why? Because whenever I'll have a A, B pair in my relation, then only I'll be searching for this B, A pair. If there is no A, B pair, then the relation by default is symmetric and I don't need to search for any B, A relation. So, if I talk about the cardinality of smallest symmetric relation, it is always 0. If you don't have any element, then the relation by default is symmetric. And what will be the cardinality of largest reflexive relation? Nothing but A cross A. If you take A cross A, it will contain all the elements. That is, for every A, B pair, it will contain a B, A pair and as well as all the other elements. So, this is going to be n square. The cardinality of largest largest symmetric relation is always n square. Now, if again we want to find out that how many symmetric relations are possible for a set containing n elements, we will again start with a small example, that is, we are having a set A with only two elements 1, 2 and we want the relation to be symmetric. Symmetric means that we should always have a B, A pair if there exists a B pair which belongs to relation R. Now, we will see what all symmetric relations are possible. So, R1, this is a symmetric relation because it is not containing anything. So, it is by default symmetric. Now, R2, it is containing only a single pair 1, 1. So, it is again symmetric because 1, 1, the B, A pair will be again 1, 1. So, it is also symmetric. R3, 2, 2, this is again symmetric. Now, let us talk about R4. R4 is containing 1, 1 and 2, 2. So, for 1, 1 and 2, 2, it is again symmetric. R5, why it is symmetric? Because I have taken 1, 1, it is not affecting the symmetric nature, and then for 1, 2, I have even taken 2, 1. So, this is symmetric. For R6, we have 2, 2 pair, which is not affecting the relation to be symmetric. For 1, 2 pair, we have 2, 1. So, it is also symmetric. If a relation contains only these two elements, that is 1, 2, 2, 1. So, for A, B, you have B, A. So, this is also symmetric. And R8, which contains all the elements 1, 1, 2, 2. Then for 1, 2, it contains 2, 1, which is nothing but A cross A. So, this is again symmetric. So, a total of 8 symmetric relations are possible for this set A having 2 elements. Now, let us talk about the general derivation, that if A has n elements, then how many symmetric relations will be possible. First, we will write down what is A cross A for such a set. For such a set, A cross A will contain 1, 1, 1, 2 up to 1, n. Same way 2, 1 up to 2, n, and the last element is going to be n, n. Again, we take the diagonal elements together. So, all the diagonal elements 1, 1, 2, 2 up to n, n. So, that means how many diagonal elements we have here? N diagonal elements are there. Or these all the leftover elements, how many elements will be these? Since A cross A has n square elements, then the diagonal elements are n elements. So, these remaining elements become n square minus n. Now, if I talk about these diagonal elements, for these diagonal elements, how many choices I have for the relation to be symmetric? I have 2 choices here. Why? Because I may include these diagonal elements or I may not include these diagonal elements. It is not going to affect the symmetric nature. But if I talk about the remaining elements, now here, if I have this element 1, 2, then it should also have 2, 1. Otherwise, the entire thing should not be there. Then, if I have 1, 3, then I must have 3, 1. So, that means for remaining elements, they will be existing either in pair or they won't exist at all. So, if I talk about how many pairs I have for these remaining elements, the remaining elements are n square minus n. So, if I talk about the pairs, the total number of pairs which are possible is n square minus n by 2. And for each pair, I have 2 choices, either to include the entire pair or to not include any element. So, for the entire pair, I have 2 choices. Total number of pairs is n square minus n by 2, and for each pair, I have 2 choices. So, how many symmetric relations are possible? 2 to the power n square minus n by 2. We have something known as transitive relation. So, what is it? If I say talk about transitive relation, so if I have my x, y that belongs to R and some component y, z that also belongs to R, then I must always have this x, z pair which should belong to R for my relation to be transitive. That means if you have A related to B, B related to C, then you should have A related to C for your relation to be transitive. We will take an example. We have a set containing 2 elements A 1, 2. Then I write down the now if I see this, I have the element 1, 1. Okay, so A, B, if I take this, then B, C, then I must have 1, 2, which is already there in the relation. So, I can say that this is basically a transitive relation. So, this way we can have a number of transitive relations which are possible. Now, talking about the cardinality of smallest and largest transitive relation possible. So, if suppose my relation has nothing, it is a empty set. So, can I say that it is a transitive relation? Yes, because when I have A, B and B, C pair, then only I will be looking for A, C pair. Otherwise, by default, it is going to be transitive. So, that means the cardinality of smallest transitive relation will be 0. And what about the cardinality of largest transitive relation? Now, if I take my entire A cross A, this A cross A is nothing but it will contain all the elements which are possible. Like for this particular example, it will have 1, 1, 2, 2, 1, 2 and 2, 1. So, this is always going to be transitive. So, that means the cardinality will be n square, because A cross A will always contain n square elements. So, that's all for today. Thank you.